So today we're going to look at more on SVD. Okay. So basically today we're going to look at SVD, and we're looking at how it can help in terms of approximating matrices, approximation of a matrix. Okay. So let's take a look. So before I go into the properties, let me write down the SVD again. For SVD, we have A of matrix size A by N, which is equal to U times M by M, which is a square matrix, multiplied with the lambda of the size M by N, and then V transpose with the size of N by N. Okay. So for example, if I have M is equal to 3 by 2, the size of 3 by 2, I'm going to have matrix U as the size of 3 by 3, right? And what is the size of the eigenvalues matrix? So what would be the size of eigenvalue matrix? Can anyone tell me?
3 by 2.
Yes, it's going to be 3 by 2, right? And for V transpose, it's going to be 2 by 2, okay? So I can write it out like this. So with U, okay, it consists of 3 columns. So I'm gonna define it as, I'm gonna write it out as 3 columns of matrix, okay. We can write it like this because generally we define a vectors as a column vectors, okay. So this U1 is gonna be, it has 3 rows, right? So it's U11, U12, U13, for example, okay? And then for the lambda is a 3 by 2, so it will be in a form like this. Oh, sorry. It's going to be 0, lambda 2, and then we have the third row, so it's all 0, okay. And then for V, okay, for V transpose, generally V can be written in terms of V1 and V2 as well, okay. For example, if V is say 1, 2, 3, 4, okay. So when I do V transpose, okay, this is gonna be 1, 2, 3, 4, okay. How do I write it in terms of V1 and V2? So this V1 is gonna be 1, 3, right? And this V2 is gonna be 2, 4, right? So how do I write in terms of V? Can anyone guess? I'm gonna write it in terms of V1 transpose and V2 transpose, okay? If you're not sure, you can take a look from up here, because when we do V transpose, we get 1, 2, okay? And then 3, 4, it means that the first row, this is the 1, 3, but we do transpose, right? From 1, 3 as a column vector, it becomes a row vector. So this is V1 transpose, and then V2 transpose. Okay, so we can write it like this, you know, in general. Okay, and what else am I gonna do? If I multiply, in most materials, they just write out what it's supposed to be, but I want to to slowly write out, so that you understand what I'm talking about. Okay, so if I just multiply these two, okay, I'm gonna multiply from the two rightmost matrices and vectors first. So this is what I'm gonna get. Okay, so the back part, I'm gonna get lambda multiplied with the V1 transpose, okay, plus 0 multiplied with V2 transpose, so it has nothing. And then second row multiplied with a column, so we will get 0 times V1 transpose plus lambda 2 V2 transpose. Okay. And then for the last row, multiply with V1 transpose and V2 transpose, we get just a 0. Okay. And then for the front term, I'll just copy them down. So this is what I'm gonna get, which is U1, U2, and then U3, right? And if I multiply together, okay, so this is one strange thing about multiplying vectors matrices, because sometimes it can be quite confusing. Okay, but here I can just multiply the row and the columns now. Okay, so what I'm gonna get is U1 lambda 1 V1 transpose plus U2 lambda 2 V2 transpose, and then multiply with 0. Okay. So in general, what we can do is like this. Okay. So in general, in general, okay, given that A is equal to U multiplied with lambda and V transpose, okay, where U is U1, U2, U3, okay, and lambda, depending on the size of it, probably lambda 1, lambda 2, and etc. And then V transpose, which is for V is equal to V1 and then V2, okay? So we can write the matrix A as the sum of, you can take a look on the previous page. So this is what it is. So we can write this A as the sum of U lambda and then V transpose. Okay. So I can write it as the summation of, I put lambda at the front, lambda of Ui, and then Vi transpose. Okay. Where Ui and Vi are uh, the vectors in the U and in the V. Okay. And I is equal to 1 to M. Okay. So if in the previous example here, M is larger than N, in that case, I guess you can just sum up to N, right? But in general, it's M, I think. M or N depends, depending on which one is larger. So if you see some the property of SVD in terms of this type of summation, don't get confused. This is what it is, okay? Actually, this is M or N, so it depends on which one is larger, okay? So well, so what do we use this for? Okay, so there are two ways to use this, but let me look at each case specifically. Okay, so let's consider if I multiply A with another matrix X, let's say X1, okay? These can be written in terms of U lambda V transpose and then X1, okay? And so what is this? So it means, so we can look at this case as a transformation, okay? It's a transformation of X1, okay? So I don't know whether I talked about this last time, but let me take a look. Maybe I talked about it, some of it already. So if we have a vector x1 and we multiply with a, okay, let's say a has a dimension of, previously is the dimension of 2 by 3, right? 2 by 3, okay? And x, okay, no need to put 1, no? Just x maybe is enough. So x is the metric vector of 3 by 1, okay? So in essence, when you multiply these together, you have the dimension of 2 by 1, okay? So a times x is the transformation or mapping of x vector, okay? And it's changed dimension from 3 by 1 to becomes 2 by 1, okay? So it's changed dimension, okay? So if you take a look at this. And in essence, what it does is, so when you multiply A with X, it's the same as multiply U lambda, V transpose, and then X, okay? Because X has the dimension of 3 by 3, okay? And this one has dimension of 3 by 1. So first of all, this is like a rotation. This is like a rotation of the vector 3 by 1, okay? And then for lambda, what it does is in lambda it has the value of 2 by 3, okay? So lambda is like this, lambda 1, lambda 2, and then 0, 0, okay? So what lambda is like a scaling, right? So this lambda, this is like more, is greater than or equal to lambda 2. So this part is like scaling, okay? Uh, for the VT, this is the rotation in R3. But then for the lambda, this is the scaling in R2. You know, it takes away the third dimension. Okay. And then when we multiply with U, this is the same as rotation again, but it's a rotation in R squared. Okay. So this is like a one way of, we can say, interpretation of what it means. Okay. Okay. Second thing, the second thing that it can be useful from the SVD is called uh, second thing is, let me see. Okay. Second thing is we can use this property, that is the A times VI is equal to lambda I UI, okay, where VI and UI are the columns of the eigenvectors, okay. So we can do, we can single out just some column vectors and multiply like this, okay. And because this is comes from, okay. And from here, what we can do is we can find UI is equal to AVI and multiply with 1 over lambda. Okay. So it means that when we try to find when we when we have a matrix A, right, and then uh, we we find the column vectors U, or non column vectors, but the matrix U, and then we have U1, U2, all the way to UM. Okay, from here we can find the vector V immediately. Okay, so this is it's gonna be equal to A times V1 over lambda 1, A times V2 over lambda 2, etc. Okay. So that's the second thing you can do. Okay. And then last one, number 3, which is the matrix approximation. Okay. So this is related to the sum. So we know that A is equal to summation of lambda I, Ui, and then Vi transpose, where I is equal to 1 to M, okay, or N, depends. Okay. So how do we do approximation? Because as you know that lambda I, as we do the summation more and more, okay, lambda becomes smaller and smaller. Okay. So we can approximate A with the summation of, let's say we approximate with K terms. Okay. So what do we have? We have I is equal 1 to K, lambda I, Ui, Vi transpose. Okay. So the important thing here is that if we have a very large matrix or large image, okay, sometimes the eigenvalue, they concentrate in only a few terms, not for the whole thing. So we can do some type of approximation. Okay. So let's look at an example. Okay. So let's look at an example. Okay. Let's say that we have an image of A with the size of 1000 times 2000. Okay. And it's a gray image. Okay. Just for how do you say it? For simplicity in computation. Okay. It's a grayscale image. Okay. So it for an image of 1000 times 2000, how many pixels are there? Can anyone tell me how many pixels are there?
2 million.
Yeah, so we have 2 million pixels, right? Or in a way, we have 2 million numbers to store. Each pixels have like one number, right? Maybe it's from 0 to 255, and so on. And then so in here, I'm saying that one pixel, just one number that we need to store. Okay. So if we store the whole image, we will need 2 million numbers. We need to store 2 million numbers. Okay. So if we store the entire image, okay, so we need to store 2 million numbers. Okay. And so based on the SVD, what we can do is we can approximate approximate the image. Okay. Well, in a way, you can think of it as a simple compression as well. Okay. So let's say that we store up to So let's say how many eigenvalues are there here? If we have a 1000 times 2000, how many eigenvalues are there? It's going to be equal to 1000, right? Okay. So let's say that we only store up to rank equals to 10. Okay. Let's say that we only concern about the 10 largest eigenvalues. Okay. 10 largest eigenvalues, okay, which is lambda 1 all the way to lambda 10. Okay. So in this case, we can write the approximation of each rank. Okay, we call approximation of each dimension or each rank. Okay. Okay. We can write like this: A1 is lambda 1 U1 V1 transpose. A2 is lambda 2 U2 and V2 transpose, and etc. until A10. Okay, lambda 10 U10 V10 transpose. Okay, and we can just approximate with 10 ranks. So we get A is equal to summation of AI. Okay, I is equal to 1 to 10. Or you can write it as summation of lambda I, UI, VI transpose, where I is equal to 1 to 10. Okay. If such a case happens, how many numbers do we need to store instead? Okay. Because we know that matrix U, no, not matrix U, the column vectors U, it has the size of m by 1. M multiplied with 1 is a vector matrix, right? So m is 1000 is 1000 times 1. And VI has the dimension or has the size of n by 1, which is 2000 times 1. Okay. So if we approximate this image with only 10 dimension or rank equal to 10, okay, so we need 10 terms, okay, 10 of this term, and each term has how many numbers we have to remember. So U has a 1000 numbers we have to store. We have a 2000 numbers to store. Okay, and then we need to store eigenvalue, which is 1 numbers. Okay, so what do we have here? We have 10 multiplied with 3001. Okay, which is 30,010. Okay, so in this case, instead of storing all 2 million numbers of all images, okay, we only need to store 30,010. Okay, so only need to store 30,010 over 2 million. Can anyone compute for me how many percent it is? Can anyone help me compute this number?
1.5.
So it's 1.5%. Okay?
Yes.
So that's the point. when you use this type of SVD, you can use it for various application. And I think last time we talked about a different way of using SVD as well, right? I think last time we talked about how to approximate a MIMO channel with the which can be of large size with the SVD. Okay, it helps in doing this type of inverse as well, right? Because let's say that you have x, let's say case 4, no? You transmit x through a system, let's say a channel or a system with with the matrix, channel matrix or system matrix A. Okay, and what do you get on this side is maybe you have noise or no noise. Let me write down no noise first, just for simplicity. So you get y is equal to ax. Okay. So oftentimes we don't know what this is. All we know is the system matrix. You can think of in communication is a channel, and then we have y. Okay. The question is always, what is x? Let's say estimate of x. What is it? Okay. So how do we find this? Uh, because A has the dimension of m by n in general, and x has the dimension of n times 1, right? So we cannot find the inverse of A easily, okay? So what we can do is we can say that, let me go to the next page, okay? So we can say that y is equal to A times x, but we cannot find an inverse of A. So what we often do this, we multiply with A transpose and y. We get A transpose times A and multiply with x, okay? And then we say that x is then A transpose times A multiply with inverse, multiply with A transpose and y, okay? If A has a very large size, then we don't want to do inversion directly, right? So what we can do is like this. We know that A is U times lambda times V transpose from SVD. And times U transpose and multiply with Y, okay? But then because the lambda, let me look at an example. Let's say it's the 2 by 3, right? So let's say it's 2 by 3. So this is gonna be 2 2, 2 by 3. Am I still here? Can anyone answer?
Yes.
Oh, I'm still here, right? Okay, I heard some sound. Okay, so we can take a look at how this reduced. You can think about 2 by 3, right? So this is the like this, okay? And so if I multiply lambda 1, 0, 0, lambda 2, 0, 0, okay? I multiply with the, oops, sorry, is the lambda transpose first, no? So if I multiply this with the lambda transpose, okay, so I get lambda 1, 0, 0, 0, lambda 2, 0. Then I multiply with lambda 1, 0, 0, lambda 2, 0, 0. And then I multiply with this again, lambda 1, 0, 0, lambda 2, 0, 0. Okay, so this is a 3 by 2. This is a 2 by 3. This is a 3 by 2. Okay. So at the end, you will get something like a 2 by, you get a 3 by 2, right? Is it right? Lambda transpose, lambda, lambda transpose, 3 by 3, 3 by 2. Okay. So this is what you will get. Okay. So what do we get? Right. So that's the question. What do we get here? So let's try to compute for fun. You can do it by yourself. Okay. I'm interested on how to reduce the term as well. So let's do from the back first. Okay. So what do we get here? So this is 2 by 3. So we get 2 by 2. Okay. So what do we get for the first term? Can anyone tell me? Okay. You can try it. You get lambda 1 square, right? And then for this term, which is the first row, multiply with the second column, you get a 0. Okay. And then you get a 0 lambda 1 square, or lambda 2 squared, right? Then if you multiply it further, you get lambda 1, 0, 0, lambda 2, and then 0, 0. So what do you get? Okay, so you get, this is 3 by 2, 3 by 2, okay? So you get lambda 1 cubed, right? And then 0. And then I think you get 0 lambda 2 cubed. And then 0, 0. Okay. So this is what you get when you multiply this term together. Anyway, so it's quite simple on how to compute all these terms. Here, I don't know, you can reduce further or you don't reduce further. Here you can write it like this. Because it's this thing, right? So you can write it, in this case, you can write it as lambda transpose and then cube. Okay. Because when you take to the power, each element is just to the power. Okay. I don't know whether I should write it like this. Generally, we write it as for the square matrix. You know, you can do power like this. But okay, let's do it. Let's do it informally. Okay. So this is what we have, and instead of to the power of m, because this is in general, this is the m by n, right? So let me do as a m instead. So there are 3 terms. Actually, it's supposed to be cubed because it's not related to the dimension. Because of these terms, there are 3 terms because there are 3 a's, so there are 3 lambda. Okay, so let me write it like this. Okay? Anyway, so it means that on the right hand side, Oh, I multiply with y, right? Okay. So instead of computing the inverse, we can compute this instead. Okay. So it means that when on this side, instead of computing a transpose times a inverse and multiply with a transpose, we don't need to do this. Okay, we don't need to do any inverse. We can just multiply with v lambda transpose to the cube and u transpose. Okay. So there's no, let's say it's a huge dimension, like MIMO system or a system with, millions of rows, millions of columns and all that. So here we don't need to do any inverse matrix at all. We can just multiply. Okay. And that's that. So lastly, before we take a short break, like 5-minute break, let me write down one more things. Okay. So in general, let me write down a diagrams for concluding what we have done so far. Okay. So in general, when we have a real matrix, okay, we can divide into two types. One is a square matrix or non-square matrix. You can think about this as A. It can be square matrix. It can be a non-square matrix. Okay. So for any real matrix, you can always do SVD. Okay. Also, you can do a pseudo inverse, but we haven't talked about it. Pseudo inverse is the case when if some of the eigenvalues are 0, then we cannot find the typical inverse, but we can just take out the dimension with the eigenvalues as 0, and then we can find the inverse of the remaining term. Okay. So for the square matrix, let's say it's a n by n. Okay. You can do many things as well. So for square matrix, you can find the determinant. You can find the trace. Okay. For the non-square matrix, let's say it's m by n. Well, you cannot do much further. Okay. Then for a square matrix, you can divide into various types, depending on how we are interested. Okay. Well, we can look it in terms of singular or non-singular types. Okay. For singular matrix, it means the determinant is equal to 0, or some of the eigenvalues is equal to 0. Okay. For non-singular matrix, the determinant is not equal to 0, so you can find a inverse. We can also look at other types as well. Okay. If we cannot find the if we cannot find the eigenvectors that are independent for some lambdas, then we call this as a defective. Okay. Defective means we cannot find the basis in the eigenvectors for some of the eigenvectors. Okay. Such that Vi and Vj's are independent. Okay. If such a case happens, we call the matrix as a defective matrix. Okay. And for the non-defective matrix, in this case, meaning that we can find the basis for lambdas, then we can divide further. Say we can call them as normal and not normal. Say non-normal and normal. Okay. So normal and non-normal here, it means that for normal, it's like normalization. For normal, it means that A times A transpose is equal to A transpose times A. Okay. For non-normal, it means we cannot, both are not equal. So that's the difference. Okay. And then, oops, I have no more space. Let me go to the next page more. Okay. For the normal case, if it's symmetric, okay, it means the lambda is always real. Okay. And it will also have the property of what is called positive definite. We will look at this a bit later during the second half of the lecture. Positive definite. It means that lambda I is greater than 0 and also for positive definite, it means if we multiplied any vectors to the matrix A, okay, this thing is always greater than 0. Okay. So this is like a definition for positive definites. Okay. Also, additionally, there's another property called orthogonal. Also, if it's symmetric, you can also find the Cholesky decomposition. Okay. Okay, meaning that A is equal to S times lambda and then S transpose. Okay. And lastly, if a matrix is orthogonal, it means that A transpose times A is equal to A times A transpose, which is equal to 1. Okay. And in here, you know, like orthogonal matrix, you can find them in unitary matrix, you know, and so on, for example. Okay. So let's have a short break, like maybe 5 minutes, no? And then come back, look at the second half. You have any question so far today? Mm-hmm. Just in case I miss any points. Okay. So like I want to emphasize earlier, the SVD is one of the most important properties and decomposition that everyone needs to know of. And in any field, you know, whether in finance, economics, social science, engineering, science, it can be in, I don't know what other fields we can talk about, data science for sure. Then you will see SVD all the time. Okay. Anyway, so please stop the recording now. Next part we will come back and to the random vectors. Okay. So the thing is, so please stop the recording now. Okay.